Yeah, I think welcome all of you to this C++ and object-oriented thinking course. I think that's a new word that I have coined because I think as it is there are too many words of this. OO words are there. Object-oriented. We have object-oriented design. Then we have the object-oriented analysis. Then we have the object-oriented programming. Right. I think for doing all these three, whether you want to do design, analysis, or programming, I'm sure you need to do some amount of object-oriented thinking. So, this is the basis for all this. So, just putting these three together, I think, is what is going to get you object-oriented thinking. Whatever that means. We have still not said what is the meaning of object orientation. I think is we need to discuss that. I think first session today, there is 1A actually. The classes are going to be like this. See, this is basically an unorthodox style of handling any course. In fact, our C and Unix course here itself is slightly unorthodox. This is going to be even more unorthodox, the way we conduct, because that's the only way I found that we can learn all of these technical aspects in that short period of time. The only way is to follow some kind of, you cannot follow the regular schoolroom, spoon feeding kind of technique. It's going to be unorthodox. There is no choice there. And secondly, we're going to have classes only on Sundays. And hopefully we should have 2 sessions on each Sunday. That means we start at 10 o'clock. Each session is about 1.5 hours. I mean, why 1.5 hours? I think is because the cassette is C90. So that is one cassette can hold one part of one session. And we take a 10-minute break. We can have a cup of coffee or a Coca-Cola or whatever your favorite poison is. So you can have that. And we come back and resettle down for one more 1.5 hour session on each Sunday. I would like to do that. I think I will do that as long as my throat doesn't give up in the center. See, that talking continuously for about 3.5 hours, I think is not a trivial task. I think so. I'm sure that probably sometime it is going to give up. In which case we quietly wind up for the day and say, come back next Sunday and continue. I'm not saying that 3.5 months must be the total duration for this particular batch. I'm not putting any kind of restrictions on that. If we need to come for the next 4 months, if we need to sit down for the next 5 months, it is all right with me, provided it is all right with you, right? So I think that should be okay. Fine. I mean, if we spread ourselves on a couple of topics, for example, it's likely that things are going to expand and we're going to take more time. The recording time is exactly live time, right? Time keeps going whether I talk or not. Hopefully I want to fill in as much as possible without leaving probably not more than 2-second gap anywhere in the cassette is my plan. But sometimes that may not work out. But anyway, doesn't matter. So what I'm saying is that we are not putting any kind of time restraints. Basically, there are 15 Sundays is the basic course right now as I see it now. But it may become more. There is totally 30 cassettes. Okay, it may become more if we want it. If it happens like that, I'm not going to take any special effort to restrict it to only 15 Sundays. Okay, so let us take more time if needed. And there is one aspect. Now the second aspect is, since the course itself is object-oriented thinking, that is the main topic itself. It is a thinking course. Thinking course means if you say we want to do some exercises, let's just look at some exercises. I suspect these exercises, of course you can do the exercises in the lab. We do have a lab facility where you can run the C++ compiler. And I think most of us are employed, so you could probably run your C++ elsewhere. Now, whatever C++ that you have, you can definitely run those compilers there and run some of the programs. I'm not saying we should not do those. We plan to do those, but then I think the most important part of an exercise itself is the thinking process, which means basically we're going to get paper exercises. Exercises are going to be mostly on paper. That means you will have to do some kind of bedside writing, So probably you've been used to bedside reading, so you'll have to do some bedside writing. Probably today, being the first session, we are just having overview of C++ and object-oriented thinking. I don't think I plan to give you any exercises for today. But then next Sunday onwards, I think we should start getting some exercises. And the only justification that you can do to the course can become a success only if you do the exercises. Just the theory part, listening to what I am saying here or looking at what I am writing on the board is not complete knowledge. To guarantee that you learn some decent amount of C++, I think the only choice that we have is to do those exercises, and they are going to be mostly on paper. You're going to sit down and write some class definition, probably. Or you're going to write down some pictures also. In fact, writing pictures You want to write one object, for example. I think object is one of the simplest pictures even I can write, so it is an object, very simple. So all of us can write that, but there are some pictures may be difficult to write. Most of the designs of large applications are shown in terms of pictures. We should be able to draw some pictures, on paper. These one bunch of exercises that we are going to work on. And doing the exercises is part of the course, part of the curriculum. And what I plan to do is, you can hand in the exercises by the end of this week, right? So that is the exercises for this week you're going to hand in by next Sunday. And you give me a few days time, couple of days time. In fact, if you can hand it in by Friday or something, 2 days time should be sufficient for me to go through each one of the exercises that have been handed in. And what I would like to do is, I would like to make some critical comments on that, So I'm going to use some bad words there, bad words, not Sanskrit bad words, only English bad words. So that means that is probably going to help you modify the way you have done those exercises. I may ask you to repeat, or I may ask you to do it in a different style or whatever. I think those comments, I think you should not take it in, you should not get hurt because of some comments. Correct? Sometimes I snatch the whole thing and then I have to do it again now. But then, I don't think we should get hurt there. The only purpose is that, we should, probably learn to think in the correct direction. I think it's the direction which is important. Object orientation. We need to orient ourselves in that direction and start thinking, start doing those exercises. I think by the end of these 15 sessions that we have, probably with a few feedbacks, you need to have that feedback some number of times, give the exercise, get the comments. Next time when you do it, I'm sure that, you will not attract the same number of comments, that should be your objective. You'll attract less number of comments. At least you will attract some new comments. Please don't keep attracting the same old comments, right? So that means the learning process has stopped. We should keep making new mistakes in life, right? So don't make the same old mistakes again and again and again. Such fellows are there. They're actually called idiots, of course. So what I'm saying is that by the end of some 3-4 rounds of this, 3-4-5 rounds of feedback, critical comments and correction and so on, you are probably in a position to do some amount of object-oriented thinking. And you can sit down and develop C++ syntax, almost the entire syntax we are covering as part of these discussions, but not in the sequence which is given in the book. Of course, the book is always Bajarn Stosrup. This is the book. I don't think you should settle for anything less than this. We just have a couple of copies in the library for reference. If you have got your own copy, it's fine, for home reading. Bajarn Stosrup, I think, version number 3 or whatever. So, volume number, release 3 or whatever. So, that's the latest, which is available. And that is the book. All our references, anything is going to be with respect to that particular book. I don't suggest you try to read any other book on C++ than original designer of C++ language itself. That is one aspect. And object orientation, I think, probably Grady Booch is one of the masters. See, object orientation, unfortunately, there are different people who have come up with slightly different looking methods of approach, slightly different methods of documentation, slightly different set of utilities to be used and so on. We do find a few different kinds of object orientations. All of them, I suppose, are approximately the same, but then I think you need to follow one, at least let's just follow one of those fellows. And a most popular approach, in terms of what is used right now in the industry is the Grady Booch's approach. So that there is one book by Grady Booch on object-oriented design. And we have a few copies of that as reference in the library. You can always keep a personal copy at home. There's nothing to stop you from doing that. In fact, many such books, I would like to have a copy at home. Whether I read or not, it should be there. So there is some such mentality that you might want to develop. These are the two primary references as far as you're concerned. And C++ syntax, like I said, we are almost covering almost 100%, but then many times we find C++ syntax is very complicated. It's very complex actually in terms of the way the compiler analyzes the statements of the program. So it's very complex. There are likely to be a lot of ambiguities and so on. What you will have to do is that's just a question of practice, that you write your program and feed it to a compiler. Compiler is the best fellow who can come back and tell you what are all the mistakes that you have made, right? So compiler is the best, is going to give you sufficient number of Gali words, and so you can fix your syntax errors and so on. So at the end of this, I think if you can also write some C++ programs which are syntax error free and probably semantic error free also. That means they actually work also. I mean, you can write some working programs. I think it's not a bad idea. You can develop some few programs on your own. There's sufficient number of exercises, I think, which are given there. We can take up that and do that. I'm not going to specifically mention saying, write this application. See, that is not, like I said, this is not, that's not my intention because this is not the approach that we are using now. We don't say, we'll do chapter 1 today, chapter 2 tomorrow. See, this is not the style of conducting this course. It's going to be slightly different. Exercises, you may have to invent on your own and do. That is one aspect. Second is, I think really we need to look at C++ really applies not to small programs actually. There's no point in doing small exercises. Let me just tell you the fact. C++ is actually suitable for large applications, okay? It's meant for large applications. But unfortunately, we cannot sit down and write one large application today, right? I mean, where is the large application that we can develop as an exercise in the classroom? We cannot do that. What we can only do is to simulate a large application, correct? We can only simulate that. And one way of doing that is to look at a couple of projects. What I'd like to do is I'd like to discuss one theoretical project which you cannot test on any of the machines. You'll have to just write it on paper and hope that it is correct. Correct, and at least try to, you can give me a copy of that and probably I can make my remarks saying that whether I like it or don't like it and so on. No? If I had given the same job to one of the juniors in the office, how I would take it, probably you're going to attract the same comments, So when you hand in your exercises, I'm going to treat as if this is an office environment. I'm the director or manager or whatever. And I've asked people to do some work and saying, well, to give me your design and you've given me the design. I might comment on your handwriting also, right? I mean, this is totally free. I'd like to retain that freedom to make any kind of comment that I want on your exercises. They're only critical comments which you should take it in the positive sense and say, let me improve, right? So that's what is there. And this, one theoretical project which you can only do on paper. And eventually I think we should also try to do some project which is practical project in the sense we can actually enter those set of programs into the machine and run it also. I'm not sure what that package is going to do. That also we need to design, right? So even the design of that application itself needs to be designed, right? So that I think eventually as the last session we can sit down and do that as a practical exercise so that we can at least make use of all the knowledges that we have accumulated in the entire course, entire 3.5 months period. And we make all of those ideas into good effective use as part of that eventual project in quotes. Is not really a live project that you are likely to do in industry, but then we try to simulate most of the work that we plan to do in industry so that it looks good, so it looks good. So we can always do that as the eventual exercise. I think since we are going to have very few Sundays, right? Sundays come once in 7 days only, right? So, and that means missing one class is we are going to miss a lot, right? So because we want to have only 15 Sundays approximately. So I think attendance is the one important issue. And I would like to start at 10 o'clock every day. Okay, so I think we should try to assemble by 10 o'clock so that see whatever I said now, probably I said something very, very interesting where people can make $1 billion or something. So some of you missed that, right? So I'm not sure of that, but you don't know it, right? So that means attendance is one very important issue. See, having assembled here, we have assembled for some reason. I don't know. In fact, I would like to ask one fundamental question. Why OOTH? Correct? I mean, why do we want to do this itself? Is the first question that I am addressing. Of course, all of us have some reason for saying, hey, I need to learn this C++ or I need to learn object orientation. I don't know for which purpose we have assembled here, but I'm sure there is some purpose. But then I'd like to analyze the correct reason for that. Whatever reason that is there, I'm saying we should do a justification for that, right? So sitting down for 4 months or 5 months trying to do this kind of a thing. See, for me it is difficult to speak for 3 hours. Let me also assure you it is not actually easy to listen to 3 hours. Listen to the same voice for 3 hours also. Even that is not a simple trivial task. So I think having gone through all that strain of doing this course for 4 months or 5 months, I think you should get some benefit in the end, right? And you will not get that benefit unless you satisfy those extracurricular activities like exercises and paper designs and running the programs on the machine and so on, other than the theory part itself. I suggest let us all try to do a sincere effort towards that direction. Maybe what we eventually learn, see, each of us, I think, we have our individual capabilities of learning. We have our individual background of what we have already learned and so on. I think eventually each person probably is not going to learn the same amount. But then whatever maximum extent that one person can learn should learn as part of this exercise. And doing that, I think we should satisfy all those conditions that I put to start with. Now let us take up this first question. Why object-oriented thinking? Right? I think the first important question. I mean, what is object orientation is the next step. First, I'd like to ask this question, why itself, Why suddenly people have started asking this? Probably 5 years back, nobody bothered about what is object, nobody knew. What is oriented, nobody knew, right? Suddenly people saying that I want you to know C++ and so on, right? C++ is, of course, is just one language, which is probably the most popular language used for writing object-oriented programs. We have had a couple of other languages, like probably one of the earliest languages was Smalltalk. Then we have a couple of other fellows like Eiffel and Ada and TLOS and so on, so class and so on. So we have a few other languages also, but then I think C++ has been the hands-down winner actually in terms of the popularity of usage. I think they've tried to throw in as much of features into C++ as possible. If you look at C++ features, C++ has got a lot of features, okay? It's got a lot of features. But then what you should do is what you are looking at is only a usage of a subset of that features as part of any application. Just because some feature is available, don't say I will go and use it now. It's not necessary that you should use all the features which are available. So because of that fact that it has provided most requirements of most kinds of object orientation. So C++ is the most popular language, so we plan to use that for our object-oriented programming. Our topic is object-oriented programming only. Then why do we want to do this? At least in recent years, it has become popular. Why? I think primary reason for this, fundamental reason, is because of the explosive growth of the software industry itself is the primary reason for that. And that explosive growth has resulted in two aspects. When you say I've got an explosive growth, that growth is in terms of number of software engineers. You take the software engineer community itself. You got a software community. Software community, I think, has grown beyond proportion. It's totally disproportionate to what it was before. It's not an arithmetic growth, definitely not even a geometric growth. I don't know, it's some way kind of exponential growth which has taken place in terms of the number of people, software people who are there in the industry right now, right? So when compared to just about 10 years back or 20 years back. And in fact, we have got people from all walks of life with vague kinds of backgrounds saying, I will do computers, right? So just take this class section. I'm sure that probably less than 20% of us are actually professionally qualified computer software engineers. Rest of us are something else actually. But then this field has attracted so many of us that this community has grown beyond proportion. If you look at the software community sometime back, maybe 10 years back or 15 years back, it used to look something like this. I just want to plot one small curve here. So we got this number of people is going to be plotted on the x-axis and some kind of a skill level, let's just take a skill level because not all computer people have the same skills, right? They've got different skill levels. And if you plotted the number of people versus the skill level that they have, what we used to find 10, 15 years back was almost a curve like this. That means we realized that at every skill level, you are likely to find approximately the same number of people. See the entries at the bottom point, right? From the zero skill, people join. And after some time, they're going to improve on their skill levels. They slowly move up in that particular curve. And there is no dramatic increase in the number of people who used to enter afresh into the software community sometime back. Of course, that means you'll find approximately the same number of people at every one of the skill levels. This was the picture sometime back. But then because of the explosive growth, exponential growth, what you find is every year, much more people enter the industry than they entered in the previous year, right? So that means the actual picture today, if you look at today's picture or the same curve, what you're likely to find is something like this. That means, of course, right at top, you still have only very few people who have that skill level, right? Right at top, approximately are the same number of people, a handful of them. And probably the topmost point here is only one person called Bill Gates. I think, correct. Only one fellow is there, right? I would say he's the most successful computer scientist, right? I mean, you just can't beat Bill Gates, right? In any respect. So he's one single point which is there, but otherwise you can see that the curve quickly spreads itself horizontally. That means as you lower the skill level, you're likely to find many more people. And in fact, if you almost reach x-axis, you'll find millions of fellows, right? Practically millions of fellows. Almost all Indians you take are capable of doing some software activity. I'm not saying they can actually write programs or whatever, but then they can be usefully employed in software industry. They can become office boys at least, right? So in a computer company. So I'm saying the entire Indian population or Chinese population, I think is sufficient. They are available at the lowest level of skill level, right? Whereas the higher levels, we still have only few people only, right? So, and where are we in this picture? If you want to know, I'll write the line also, no problem. We are, I don't think we are quite at the x-axis level. We are somewhere here, I think. So I'll just put it there. So that means we are good C programmers, but then unfortunately we find there are a lot of other good C programmers also, right? So what we would like to do in our life is to slowly raise our own skill level, higher and higher. That is our attempt that we want to do. That is one aspect. Then this curve also has got a very important aspect or effect on this project management actually. In fact, I think object orientation addresses is not programming. Anybody can write programs. Anybody with sufficient experience can write tons of C programs or Fortran programs or COBOL programs, right? Programmers are dime a dozen. Nobody's worried about programming. Actually, the management of that programming is what is the key aspect. How do we manage a project? Correct. And the other aspect of the explosive growth is, one is the community, other one is the program size itself. Take program size. Program size in the early days when I entered the industry about 20 years back, 20 years ago, was that we used to write a program which are 1 kilobyte, huge program, or maybe 2 kilobytes and so on, right? So is the size of the program that we used to write. Whereas slowly later on, what happened was people started writing some several 100 kilobyte programs, like 200 kilobytes, 100 kilobytes, 300 kilobytes kind of programs, 600 kilobytes kind of programs they started writing. And then again, I think slightly later on, maybe another 5 years later, we found that people started writing 1 megabyte program, 2 megabytes is the size of the program and so on. And of course, today I think it went to some 20 megabytes. Probably if you take a Windows 2000 or something, I don't know if there is such a package which is going to be developed by Bill Gates, or maybe it's going to be called Doors 2000 if I am not very wrong. So that is going to be some 100 megabytes is the size of the program, or maybe 200 megabytes, right? So you can see the size of the program also has been increasing dramatically, explosively, exponentially in the past 5-10 years. 5-10 years, we have seen that kind of growth, sir. That means now you can see that when you say we are doing a project management, if you look at that small program like 1 kilobyte, 2 kilobyte, call one idiot and say idiot is actually a smart fellow. Okay. So in my discussion, when I say idiot, don't think I'm using a bad word. Idiot really means very smart fellow. Call idiot and say, why do you write this program? He will go there and write it and come back. I mean, one fellow is sufficient to develop such small looking programs, right? So you can actually lock him in the office and say, till you write it, I'm not going to let you go, right? So I mean, this is not a joke. This has been done before. In my time, lock some 3-4 fellows in an office and say, you're not going home till you finish this particular package, right? So, because they're reasonably small, we could do that. But when you go to some 200 megabyte program, it is not going to be one person who's going to be developing the code. You're likely to find hundreds of people, hundreds of software engineers who are going to be developing this code. Obviously, we need some kind of management, right? So definitely. So management is going to be difficult for large projects. In fact, in say program sizes, we have this small size programs is what we used to have, correct? These are small size. Then they became, I think, medium size is several, couple of 100 kilobytes, you can say, is some medium size program. This 1 megabyte and 20 megabytes is something like a large size program, very large programs. And this is not even large. You should probably call it colossal, right? Colossal kind of program, right? So, colossal size. Just unimaginable. You can't comprehend it. Our brain cannot comprehend that size of that program, that vastness of that program. Exactly like you cannot comprehend the Chinese population, right? It's just impossible to make out. Even Bombay population, for example, if you want to just a glimpse of it, just watch one of those stations now. Railway stations. At the time one train stops and you just see how many people keep coming out, there is no end to that. Cinema theaters also people keep coming out, but then after 2 minutes the whole thing is empty, it has thinned out the population. Whereas railway stations, I find, you just keep on, I was fascinated. I was standing for half an hour. There is no reduction in the amount of traffic, man traffic, which is going to come out, human traffic. So that means, we can't comprehend that kind. Just imagine such fellows are there everywhere in India and China and so on, right? So something similar to that. These are colossal. Colossal is, there is no answer to it. You just don't understand. I think fundamentally you can say the size is something which we don't appreciate, we don't understand, right? It's something like saying $1,000 billion. You can say it, but I'm sure we don't appreciate that amount of money, right? what you can do with that money and so on. It's just impossible to imagine, right? So that kind of sizes which have come. Of course, why program sizes have grown is a question which we will have to address sometime, slightly later on. I'm only saying that program sizes have grown, right? That's a fact. And number of people have grown is also another fact. And that means that one package or a project, for example, today, it is not going to be developed by one single person. Definitely not. No questions. It requires a fairly large group. And when you got a large group of people, obviously not all the fellows are going to be top-notch fellows, right? So you're likely to find one small set of fellows who got fairly higher skill levels in project management, senior fellows, and who are going to manage this group of people. We get hundreds of fellows at lower skill levels, and this is how projects are going to be developed, right? So, and obviously these fellows are likely to make mistakes. No questions, because they don't have the same skill level, right? They're going to make mistakes, and first of all, why do we allow them to make mistakes? And how do we correct those mistakes? Correct? Remember, testing, we can do program testing. But then program testing, today these programs are so complex that there is no way you can do 100% testing of all inputs and all outputs for any kind of program. It's not possible, right? We need to certify a program without 100% testing. We have to make sure that the development itself is alright. And how do we make sure of that? We find that the usual methods that we've been using, usual language techniques that we've been using, or usual methods for design, they don't scale very well for such large applications. Therefore, there is a need for object orientation. Right? Object orientation is a method which scales well. This is called scaling. I'll just give a simple analogy. We know how to make some 4 dosais at home, right? You can make 4 good dosais at home, masala dosais. Unfortunately, the method that you use to make dosais at home does not scale well. I'll just ask you to make 4,000 dosais. Let us go and market it. No, it doesn't work. Sorry, that method it does not apply. No, it doesn't scale well for large size. So the traditional methods of design, even structured programming design, top-down design, bottom-up design, whatever kind of designs that we had, unfortunately, they do not scale well for such large applications, such colossal size of applications, right? Even with the large applications, people have faced quite a few severe problems. In fact, you can see that C++ is C, no questions, but it is a better C, right? I mean, the C had some problems even with large applications. Forget about trying to write a colossal application using C. Not even attempted, right? So, even with large applications, we had a problem. C++, I think, is just addressing the problems of C in the case of large and colossal kind of applications. That is all. C++ also is a C only. Not much of difference in terms of syntax. Original syntax is the same. It's a superset of C, right? So, would like to use that. That means we realize that for scaling, for development of large projects, we need some new style of design. We need a new style of analysis and so on, right? So, that is because the programs have grown in size. Now, next question is why programs have grown in size? I think the next aspect is saying, why do we need to write a 200 megabyte program today? Remember, these programs are also addressing some kind of real life issues, right? And programs are not in isolation. They are developed for specific applications. If you take any live application, for example, they are very complex. No? You take an air traffic control system, or you take a wire control for an Airbus, for example, so that is a complicated stuff. Or you take an imaging system, or you take a industrial robo which does manufacturing, or you take a computer-aided education or manufacturing or design and so on, right? You look at any of these applications, what we are likely to find, or take a large database, a database of pagers or database of cellular phones or database of vehicles on the road. You take anything, database of roads in Bangalore. You understand? See? In fact, you can see that the way the repairs are conducted to these roads, the way BCC or BDR does the repairs, does not scale very well for tomorrow, right? And how are you going to handle all those millions of vehicles which are going to come next year, right? The number of vehicles are growing at an explosive rate, right? So that means this does not scale well. I mean, I'm sure something is not going to snap sometime. I guarantee it. Probably it has already snapped, right? So in terms of the traffic. So that means we need to use an approach which should scale well for larger and larger sizes, right? That requires object-oriented thinking. And these programs have grown in size because they address real-life problems which are massive. No? Real-life programs are very large, very, very complicated, right? They're very complex. That is why these programs size also is very large. Then how do we solve that? And what is this object orientation becomes the next aspect. No, real life, when you say I take one industrial robo and try to write a program for it, or write one expert system, write a doctor program which can diagnose any kind of disease and so on. You can think of that. Definitely it is very complicated. No questions on that. I mean, forget about writing a computer program. That is the next step first. First thing is you need to understand what is that is the system itself now. Unless you understand what a robot is supposed to do. Remember, today you have a robot. Tomorrow, supposing you don't have a robot, a human being actually has got to do that work that the robot was doing. No? Tell me what he should do. That is, first thing is, I think the comprehension of these large applications itself is not possible. One person cannot comprehend how the entire system is working. Forget about writing a program for it. No? Our human brain cannot comprehend such large systems. I can give you a couple of examples. Take one foreign bank. You can just visit it anytime. You just go in and come out. You see a lot of fellows are there, all wearing ties, and maybe he does a couple of signatures and maybe crack a couple of jokes with his secretary. And at the end of that, he comes home. Now, I mean, what is he doing? What is his banking business? We can't appreciate it. I mean, I don't know what he's doing, man. In fact, I have tried to follow this foreign bank business sometime back. Just look at all the fellows in the bank, right? What all they're doing. Watch them for 1 month. You still can't make out what is it they're doing. We don't even understand. Our brain cannot comprehend the banking business. Banking business is so complicated. In fact, anything is very complicated. Then first of all, forget about writing any programs. How is our brain managing today? Today we say I have to go to the city market and come back. It's a big program, right? For the brain. It's big. You understand? How is the brain managing? Brain uses a very, very simple technique for this. It uses what is known as abstraction. The basis for object orientation is abstraction. No, abstraction. Now let me just show you what is the meaning of abstraction. In fact, object itself is an abstraction. So the fundamental basis of object orientation is object, right? Objects. We got objects. Real life has got objects. Our programs are going to have objects. An object basically is an abstraction. Now what is abstraction? In fact, if you look at an object has got a set of properties, right? Any object you take, take a cow for example. Cow has got a tail, has got 4 legs, it gives milk, it eats grass, correct? It's got some color, correct? So there are different properties for the cow. But when you say a cow, for example, what is our brain going to think of? Are we worried about the color of the cow? Yes or no? I mean, if the cow is green or black, green cows I don't think are there, but black or white or red or something, we are not interested in the color of the cow. What is my interest in a cow? For example, I might probably look at the cow and say, I think she is going to eat a lot of grass, but probably she'll give me milk also, right? I'm more interested in what grass the cow is going to eat and how much milk that I'm going to get, right? Other than that, the length of the tail of the cow and so on, I'm not sure I am interested. So if you take any object and a set of properties, there is one set of properties which are called essential properties. The essential properties, these are non-essential. Non-essential, of course, this essential, non-essential of an object is basically, I mean, if you ask the cow, I'm saying cow says, no, for me tail is very important because I need to swat flies, right? I mean, for the cow itself, probably tail is very important. So this essentialness comes not from the object, it is from the point of view of the observer. So you got an observer or the viewer. Viewer wants to use this somebody wants to use this object, for example, and whoever that somebody is, perhaps it's going to be other objects. We ourselves are objects, As far as cow is concerned, a man is an object, correct? And whenever he is wearing sari, is alright. Otherwise it is not alright. So that's what a cow is going to think. Sari, the human being is alright, Otherwise I'm going to kick. See, that is a cow. Cow also thinks in terms of human beings as objects. I'm sure of that, right? So, I mean, we can't verify that, I suppose, but so, the essentialness of the properties actually depends on the observer, right? So, and our brain only observes what is essential for our purpose. Correct? One more analogy. Look at the clock there. When you look at the clock, of course, clocks you get in varied shapes and sizes. You get round clocks, square clocks, quartz clocks, correct? With a winding, which is there, this, what do you call the mechanical clocks and so on. You get different varieties. But as far as we are concerned, a clock should tell the time, right? I don't care how he maintains the time. Inside, probably there is one fellow who is turning the needle also is alright. I mean, what is your problem, no? As long as the clock can tell you the time, we have no problem. So our brain, when you say a clock, whereas a clock repairer comes and looks at it, another fellow, here is different. He says, this clock, sir, is not good. Why? How do I take it out for repair? He is trying to take it out for repair, no? See, you understand? Similarly, when a veterinary doctor looks at a cow, Probably he's going to make a few observations. Let me not even wild guess those. Okay, so you can guess what he wants to make, which is definitely his thinking on essential features of a cow are different from our thinking of essential features of a cow, right? That means each object has got lot of features, lot of properties. But then out of that, only some part of it, very small part of it, is of interest to us. We are the observers. We are the users of that object. What you have to do is you have to focus your attention only on those essential features. That whole bunch of essential features is called the abstraction. Therefore, what is a cow? A cow eats grass, gives milk, correct? Does not bite. Might, of course, give you a kick or two once or twice. See, this is a whole bunch of properties, I think, is sufficient to say there is a cow, no? You understand? That means each object has got that set of essential properties as far as a viewer is concerned. And a viewer should focus only on those aspects of the object and not anything else. Object may contain lots of inner working details. So, when you say I've got an object, actually, object, really speaking, has got two aspects that we need to look at. Say I got an object. Object has got to work. Clock has got to have some kind of a mechanism inside, has got to have needles, has got to have a frame, has got to have a lot of things, right? So, it is designed like that to work like a clock. It's got some inner working detail, you know. It's got some inner working detail, the way it works. I'm sure the cow has got a couple of lungs and so on, right? So, probably it's got 3 lungs. We may not bother also. Whether it's 3 lungs, 2 lungs, doesn't matter. No? I mean, whether the cow has got 1 kidney or 2 kidneys, I don't think is material to us. We don't care about it. But of course, cow cares about it. So the inner working detail, which is what is known as the implementation of this. It's called implementation. Because this is how the object is implemented. Whereas actually, you can see that other fellows, really speaking, actually, in terms of object-oriented programming, what you really have is objects only. There is nothing else. When you say viewer is another object, right? So, other objects, if you look at other objects, for example, what they want to look at is only those essential features here, is what is known as the interface. This is called the interface. So, interface of an object is only a very small part of the entire object itself, right? And we would like to keep this implementation as different, or rather as independent of the interface as possible. Of course, it is the implementation which is giving the interface. It is the quads inside which is giving you that movement of the clock, right? But we would like to keep that independent, fairly independent, as independent as possible. So that the reason is very simple. It adds to maintainability of the program. Tomorrow I can change this implementation. I don't like this implementation. I'll take away the quads and put something else inside the clock. And all the rest of the people are still going to be happy because the clock behaves like a clock, no? I mean, see, there is always, these essential features also has got what is known as an expected behavior, no? Expected behavior is there, no? Interface is basically the expected behavior, right? Suddenly you're not going to find one lion walking in and eating grass, no? I mean, it's not expected of lions. So, when that happens, in fact, this is also known as the principle of least astonishment. Least astonishment. That is, other objects should not be astonished. They should be least astonished when you change the implementation. That means interface should be kept as same as possible. You have to keep that as same as possible. And when you do that, what happens is, that means this program continues to work. When you change the implementations of objects, inner working details of the objects, which have got a large application which is only made up of objects. Now you can see you can change parts of it without really affecting the rest of the code itself, right? That is the basis for object-oriented programming. In fact, when you look at a large application, let's just take a large application. Large application, maybe a couple of 100 megabytes or even 2-3 megabytes of code that is there. We find that there are a lot of code here, right? I mean, a lot of programs and procedures and so on. But then there are some key procedures, right? So there are some small packets of key procedures, correct? There are a few key procedures. And these key procedures are responsible for getting you the kind of response times or the speed or the maintainability or the behavior of the entire package and so on. See, the entire, the key functionality of this entire package depends on some vague key areas, very small areas which are part of the entire application. So what I suspect is going to happen in the hierarchy of people who develop it. Remember, the project group is always going to be like this, right? It's always going to be like this. These top fellows here, I suppose, are going to focus only on those key areas, right? And leave it to the bottom fellows. And I got a number of fellows, all that piece of code you please go and develop. As long as you don't tamper with this small piece of code, I think you got a reasonable chance that the entire package is likely to work on. Otherwise, When you develop some 2 million lines of code, colossal application, I'm not sure it is going to work, right? I mean, our 20-line program does not work in the lab. So how is a 2 million line code going to work? Correct? It has got to work. The way it can work is this. There are some key areas which is basically going to be addressed only by some senior, very experienced people with vision and so on, right? Whatever that is. So such people are going to address that, and we make sure that the other people basically handle only the rest of the mundane details. That is 99% actually. Detail is 99%. Is something like, I'll give an analogy, something like our brain works. Take brain for example. Brain is the master of our body, correct? Brain says, look boss, I don't want to control everything. Let me control the most interesting and the most difficult processes. Thinking process, logic. Only I will control, man. Now walking, running, this motor process now, of this, let me not worry, let us give it to a lowly fellow like spinal cord and so on. I'm sure spinal cord is going to make a mistake or two when he's walking, right? So, he's going to make a mistake or two, then we'll throw him on the head and fix it, don't worry. When these people make a mistake, I'll throw him on the head. But let us leave it to small little fellows, like the kidney and like the, whatever other organs that we are likely to, we are going to have, or we are having, I think. So, I'm saying, brain says, I'm not interested in controlling all of those. I'm going to control only the key parts of it, correct? Key part of the logic. That is a very small part actually. You can see that the size of the brain is negligible when compared to the size of all other organs put together. But then brain is the brain, right? So you can see that that's how the brain works. Otherwise you cannot make the human body work, correct? Distribute the responsibilities equally throughout the control of the nervous system does not work. That is how these, all these animals, they have no sense at all, right? So, whereas brain, you can see human brain is that power only because it is only doing the interesting part. An interesting part is being interested. And an idiot makes a mistake, this one will correct it also. He's going to correct it, right? So he's got that control. He's got the eventual control is there in the brain. So the same way, we would like to keep the eventual control of the programs, correct? And make sure that the juniors, so to speak, do not tamper or do not affect the way these key areas work, of course. And of course, this, making sure that they don't do this, is something which we can do definitely by a discipline, right? That means you can have a programming discipline. Programming discipline in the office, for example, as part of this project development, you say I can have a programming discipline saying that, look boss, this particular file only I edit. You people know edit, right? Don't edit. All these files you edit, correct? So you can always have such discipline as part of this office. And when you follow such discipline, definitely even a C language can be used for development of object-oriented programs. No questions, sir. C can be used. I'm saying C is a language which can be used for development of object-oriented applications. There is no questions on that. But then you require massive amount of programming discipline, which is outside the language, right? Whereas, we would like to have a language. Language should actually enforce this discipline. Should enforce this discipline. C++ does that, you know. It enforces that if these people try to do something to this piece of code or data, whatever is their key areas, fellow will stop. He says, sorry, you can't do this. No, it is enforced, right? So, it is that enforcement which makes it easy for us to use C++ rather than C for development of large applications. Otherwise, whatever you can do in C++, you can do in C. No questions on that. Absolutely no questions on that. Definitely you can do it in C, but then that is much more cumbersome. I won't even say complicated. It is actually more cumbersome and subject to errors. Whereas C++, the compiler itself will catch a lot of our errors. That means that is the advantage that we get by using this object-oriented style of development of program itself. So that is the need for object orientation is because we got these applications which are very large. But then how our brain works on those applications, because our brain is tackling such problems every day. In fact, the best object-oriented approach is the way your own brain solves problems in life. That is analogy actually. You can see how you work, your brain works. Simply try to imitate this, exactly what the brain does. I think you would have developed one good object-oriented application. Right? No questions on that. So that means when you have got a very complicated system or complex system, what is the brain going to do? One aspect is look at abstractions, I think, and form objects out of it. So we're going to look for only essential features of objects so that we can focus only on those ideas. And secondly, it also adds to you can change the implementation of the objects at a later stage. It adds to what is known as resilience of the software. No? Resilience. See, software should not break down just because you're going to change 2 lines of code, right? So it should be resilient. It should be resilient like the human body. You cut off one finger, I'm not going to dive in. I'm still going to continue to work and practically do everything that I want to do, right? Maybe if you take off my eyes, for example, I might be affected more severely, but I'm sure that this brain can work out some scheme of getting back to business, right? So, and I'll just quote one story, not story, on live analogy which really took place. In our village, we have a gentleman who's born blind. Okay, no question of having eyes and being taken away. He's blind actually, born blind. He's slightly older than me, so he has not seen anybody in his life. Okay, and of course, but then his brain has worked out a scheme of recognizing people. Right? So he's basically, I think, he uses the tactile sense. Tactile is he'll just hold your hand. You know? Just hold your hand and say, "Oh, Shastri, when did you come?" Oh. Or hold somebody else's hand. "Oh, Satish, when did you come?" And so on. So, he can immediately recognize all the people in the village, but just that brain can make out that. So it has substituted that vision with the tactile aspect. Right? So it is resilient. Right? That's what he used to tell us now. In fact, we don't visit our village frequently, once in 5 years, 10 years. Correct. And we go and hold his hand, he says, "Hey, what is this man? You fellows don't come at all. When do I see you? I saw you last time 10 years. He has actually not seen me at all. He said, "I saw you only 10 years ago." Right? Immediate, instantaneously he will do that. Right? So one day we wanted to play a trick on this chap. So we had one gentleman who was born outside the village. He has not gone to the village at all. In fact, he has not seen the village. This fellow has not seen him in court. And we just took him there and asked him to hold his hand. He held his hand and said, "Look," he said, "Hey, it's slightly confusing, man. This fellow is confusing. He looks like that fellow, but not quite that fellow. Looks like this fellow, but not quite like this fellow." He's actually telling the whole family tree there. No? He's just quoting all the members of the family, saying that he's quite like that fellow, but not quite. You know. So you understand? His brain has adjusted itself to such an extent. He's so resilient, so robust. Correct? Human body is very robust. Correct? It's the main artery from the heart breaks down, heart to brain. Correct? If fellow will open up one more is there. I definitely simply puncture one more wall and say I'm going to pump the blood. Correct? Is that? That's very, very resilient. The software should be such resilient stuff. Take out one piece of software should still work. I'm not sure it is going to do, but at least get some stupid junior to go and modify some piece of code. Program should work. Almost correct. Maybe one or two mistakes it might do, but it should not simply crash and fall down on its feet, right? So, fall down on its face, so to speak. So, we need to write resilient software. Resilience comes only from this almost independence between interface of objects to other objects and the inner working detail or the implementation of the objects. That's one of the key aspects of abstraction. So, abstractions, that means all what other objects need to know are only the interfaces of objects. I don't want to worry about inner working detail. Then even if you change that, it's not going to hurt me, right? So what you don't know can never hurt you if it changes. What you know changes can definitely hurt you, right? So this is also known as hiding, no? Information hiding, or sometimes also known as encapsulation. This is also known as encapsulation. Encapsulation is we would like to hide the implementation detail, working detail of an object from the interface. Now, we'd like to hide it so that inner working detail of an object changes tomorrow should not affect other objects at all, right? So that encapsulation, after abstraction, you need to do encapsulation. And definitely in C syntax, you can do encapsulation saying that I want to change it, you know, this structure I want to change and so on. But then that manual discipline will break down sometime in life, right? Whereas you would like the language to enforce this encapsulation. So you'd like to use these object-oriented programming languages which enforce this abstraction, which can enforce this encapsulation, so that when you develop the program, it becomes that simple to manage. I think these address management of programs more than programming. Programming we are going to still do in the old traditional style of writing C syntax. C syntax is still there, right, as part of C++. So it's only the management which is going to be different, right? So that is what we would like to look at. Now, when you're doing this object-oriented design of objects, for example, there are different development models or design models that we need to understand of an object. Is actually the question of its behavior, how we need to address it. Now, in fact, there are three orthogonal different dimensions that you need to look at. When you say I want to look at these design models, no, three different orthogonal dimensions. One is, so we got the x-axis plus x and minus x, of course, are two different aspects. One is what you say is that static behavior of an object versus the dynamic behavior. Dynamic behavior, that means remember, statically, when the object is stable, in a stable state, it is supposed to have some set of values, right, sir? The object is relaxing. Object at equilibrium is different. Object dynamically is different. No, dynamic object is not in equilibrium. No, in between is actually his center of gravity. Everything is gone. You can see that. That means what is the dynamic behavior? How dynamic an object is an analysis and a design we need to take care of in development. Static is when the object is at rest. Of course, it cannot, suddenly I can't have a couple of horns here, right? I mean, that is not Shastri, right? So, and you will not be least astonished, you will be most astonished, correct? I should not grow a couple of horns. See, that is the expected behavior. You expect some behavior from me, right? And that is MLA Shastri as an object actually. Your brain actually is looking at me as an object, right? Test is very simple. As long as you are not astonished at the end of the class, I think he is alright, right? You suddenly get astonished, then I think I have done something which you thought I was not supposed to do, correct? That is the abstraction. You abstract everything in life, right? Our brain does that. All the time it is doing it. It is only for us to recognize it. So, static is when the object is stationary, what are the properties that must be satisfied, what are the values, any data boxes that is there, what they should have and so on. You need to make sure that they are correct, first of all, in the design itself. Then dynamic, I think, is little more difficult because object is changing. In the center, you may have some vague looking values, but it's going to restore back, by the time you catch the object once again, right? So, dynamic objects are always a bit difficult to handle than static nature of object, definitely. No questions on that. Similarly, we have other model is, one is what is known as the physical model of the object. I mean, physically, what does this object look like? Now, physical components is one. But then many times what happens is not just a physical entity which is making that object. There is some surrounding logical impression also for the object. Is basically a logical aspect of the object also. So you got another axis actually. So there's some logical aspects. Correct. Part of the object may be in terms of the way object works itself, right? So the logical aspect. Physical always does not tell you the entire story. You may have to look at the logical aspect of the object also is another dimension that we need to look at when you say I want to look at objects. And lastly, of course, we have what is known as a class. Class, I have not introduced this class. Class is the basis of C++ programming. Class is what is going to introduce objects in this C++ language. Class specifies that expected behavior. Is the abstraction actually. Class is the basis for abstraction. Is one way of looking at it. Other way is to look at what are called modules. Modules is, that is an object can belong to one class but to another module and vice versa and so on. So you look at objects. Actually objects are at the center of this sphere actually. That means there are different properties or characteristics of the objects which reflect static or dynamic properties or physical and logical characteristics or maybe class and module characteristics of the objects. And when you are designing one large application, each object, you must always think of all these three combinations, These are actually called development models of thinking actually. So you should always think on all these aspects before you say, yes, I will go and write the program. You should understand the dynamics, statics and so on, right? So that is one aspect that we need to keep in mind. Now, another aspect is this object-oriented thinking, like I said, has become popular in the recent years, probably in the past 8 years only. Because of necessity, of course, because the application sizes have grown. And how is it that, how do we reach this place? What is this evolution of design methods now? Some kind of a historical picture that probably you'll be able to appreciate it. Historically, how are the different design methods have changed, right? Some time ago, people were saying this structured programming is the method that you must use, the best method in the world, correct? In fact, some time back, I was saying C is the best language. Correct. I mean, at that time, it was correct. Today, it may not be correct, right? So, because everything is going to evolve, right? So how the object-oriented methods have evolved over a period of time. Let me just trace that approximate history. It also give you a good idea about how this object orientation design itself works. I think give at least some rough picture of that. Is in the early days, we had what are called the first generation languages. First generation languages, probably you have this Fortran 1 and maybe Fortran 2 and so on, right? Fortran 1 and 2 are what are called first generation languages. Earliest languages which are designed on computers. And people used to write also the kind of programs that people are writing. If you look at the number of lines of code, see, number of lines of code is only a quantity, does not really measure the size of a package. But then, at least as a ballpark figure, at least to appreciate that fact about the number of lines, let me just quote some figures there. They have no real significance. Something like saying, I've got 1,000 lines, 1,000 lines of code or something. So, you can happily write write in such first generation languages, it works. And how these, what is the design model for this? Language model itself is very simple. Remember when you say I've got a program consists of several instructions, right? Several set of instructions. So you got these instructions, which actually what we call procedures in C, or what we call subroutines in Fortran and so on. Whatever you call it, doesn't matter. You got a set of statements, right? Set of statements which the compiler is going to translate into a series of machine language instructions. Correct. So that is the set of programs that you have. These are sub-programs, right? Sub-programs. And what they want to do is they want to operate on some data. The program by itself doesn't do anything. Instructions have got to access some data. I've got to modify some data. Maybe add a couple of numbers, subtract the numbers, and so on. Run some algorithm. He's going to operate on one bunch of data. So you got a whole bunch of data. Data are some data boxes, and these programs go and operate on the data boxes, right? In fact, there is a whole set of global data on which all the programs can go and operate. You understand? This is something similar to an Hindu undivided family. That means there is one general kitty there. Money is kept in one leg box on top. Anybody wants money, put your hand into that same box and take it, right? So data is single place. But here the catch is, you can see that this does not scale well to even slightly larger program, saying that I want to write on 10,000 line program. I think you are in a bit of a trouble, no? Hindu undivided family is alright, provided you have some 4 or 5 members in the family. Somebody got some 52 members or something, is a problem, right? So you say tomorrow morning I have to pay the exam fees, right? So let us make sure money is there. Money is there, no problem, right? So next day morning, get up and put your hand in, money is disappeared now, because I don't know who, out of the 52 fellows, probably some 2-3 fellows quietly went to a night show or something, right? So live show, dead show, anything. Correct? So that means this does not scale well to even slightly larger programs. People face difficulty saying that, look, but this is dangerous. If I want to pay my exam fees, what I would do? I'll take out that money, it's still an Hindu undivided family only. That kitty is there. I'll take out that money, put it in my purse, put my purse in my pocket and sleep on it like this. You understand? So that tomorrow morning I know it is there. See, this is my money, my personal money, which is different from public money. So I would like to have some private data. So that is the second generation languages. What they have is, you have these programs. These programs have their own couple of small data. Basically private data. So these instructions can access these data, but of course they can also access the public data. That is still there. Public is still available. So that is the second generation kind of languages, which people had. And probably you can write, I'm saying writing 10,000 line program is a bit difficult task there. Probably 5,000 lines is alright. You can manage. Is manageable sizes. Anything more than this, I think we are in big trouble. Correct. So we need to go to the third generation languages, which is basically C. C is the third generation language. C and probably even Fortran, for example. That is Fortran 4. Fortran 4 or Fortran 37. These are what are called modular languages. So modularity is another aspect of evolution, language evolution which has taken place. And modularity is another aspect of object orientation itself. Modularity is also part of this. We learned that lesson in the C days, but then we continue to use it as part of object-oriented programming. So modularity is definitely a must. So in this case, what happens? Probably you're talking of some 50,000 line program or maybe 100,000 line program and so on. Definitely you can't write a second generation kind of program for it. It just does not work. See, remember, as soon as you say it is 100,000 lines, it is not one programmer who's going to write the programs, right? So here probably one programmer can write the entire set of programs. So it is easily manageable. As soon as you go to anything more than 100,000 lines or 200,000 lines and so on, definitely one programmer is not going to write those many lines of code. It is going to be on a group of programmers, maybe 5 programmers or 10 programmers. Then definitely there is a programmer interaction which is going to be a problem, right? So, and probably what you want to do is, modularity is very simple. What we do is, we got the same set of programs, of course, same old picture, except that I'm going to split that set of programs into several modules, right? So there are several modules. I got one module which might have its own private data, another module, its own private data and so on. Same. The picture is the same. And we still have the global set of data. The global data are there. And these modules, of course, can access the global data. Right? No questions. They can also access their local data. And occasionally, these fellows may also want to access inter-module access also. That is, data of another module I may want to access. Right? So, you would like to do that. There is some kind of interdependence. Right? These are not totally independent kind of modules. There may be some dependencies. Of course, the best design of modularity here is, see, each module, of course, is what is known as a physical file in the operating system. It's a separate file. And use a linker to link up together and produce a final program. And each programmer probably is going to develop 1 or 2 modules, correct? So that way we We distribute the task. We manage that project by distributing the task of doing different things to different programmers. And each probably is one functional entity, is doing one kind of job, probably can be handled by one programmer and so on. So modularity is a very important aspect in terms of project management. And when you do that, of course, if there is too much of interdependency of modules, then we're going to have a bit of trouble, because saying that I change one small line here, his module does not work. You see, that should not happen, right? So when you change here, probably this doesn't work, that other fellow should continue to work. We need to have a good amount of resilience in the software. How do we achieve that? Is to keep this intermodular interaction to minimal aspect. No? Intermodular interaction should be minimal. Always. It's very, very important. By keeping that minimal, I'm sure you can't avoid it. If you can't avoid it, at least keep that very, very minimal. Then obviously it's going to give you greater and greater resilience. Okay. It's going to give you a greater resilience for this. Now this works quite well for such size applications. People have managed such projects, no questions on that. These are basically large programs, but then they're not colossal programs. You might want to develop a package which is 2 million lines of code or something. It's going to have some 1,000 modules. It's going to have some 2,000 programmers. I think this method, this traditional method of structured programming method breaks down. So even this cannot be used for that purpose, because this style breaks down, you know, when you scale it up to very large, colossal size of applications. What we require is the object-oriented model of development. How is that going to work? Let's just look at the object-oriented style. You can call it a fourth generation if you want, whatever that is. Or the O style. O style is very simple. What it is, we develop the programs not like this. We develop the program in terms of objects. So I got one object, I got another object, correct? Object, I got third object. So you just have a set of objects, a number of objects. And obviously there is an interaction between the objects, no questions, correct? And of course you like to keep the interaction minimal. As long as you keep the interaction minimal, you're doing fine. There is an inner working detail for the object. That is, each object itself may have a set of instructions and may have a set of data boxes also. Each one has got its own private data, correct? And a whole bunch of text segments, right? It's got the instructions. But then inner working detail is very tight. That means each data here depends on another data, each instruction depends on another instruction, so on. There is a lot of dependency within this object. But then across objects, from one object to another object, we are only looking at the essential features. We are only looking at the interface. Correct? We don't care about the inner working detail. It's going to give you that resilience. That means you can see that one object can be designed almost in isolation. See, that is the advantage of object-oriented thinking. Keeping this interface minimal is, each object can be designed almost in isolation. I'm saying not 100% isolation, because it does depend on a couple of other objects. But the dependency is so minimal that we can try to practically design the entire object by itself, design another object by itself, and then say just provide that small interface, correct, between objects. That is how this object-oriented thinking itself is going to work. This is for very large applications. Let me just put some figure here. Very large application, which probably say from 1 million lines of code or something. 1 million lines. Probably this scheme is manageable. I think it's still going to be difficult, but then it's probably manageable. Definitely this would not have worked. The old style would not have worked. But then this is only very large. This is still not colossal. I might be looking at some 4 million lines of code or 5 million lines of code, even much bigger than this, in which case even this scheme is not going to work very well. But then it scales well. That is, the same object orientation we would like to do is exactly the way our human brain also works. When you say I've got a very complex system, no? Very complex system, how the brain is going to work. In fact, the entire universe itself is so complex, right? The way anything works in the universe is very complex, right? But then our brain seems to do business with most of the aspects, correct? You understand? Take this I'll just take any example you can take. Right now you can take any example. I'll take this microphone. This microphone, I'm sure it's got a lot of characteristics, right? It's got that tension, it's got that plastic, it's got that material, which have got some carbon atoms, oxygen atoms, correct? Oxygen molecules, correct? It's got protons, electrons. It's got this microphone, I don't know what else it's got. All these put together is a microphone. But then as far as an observer, as a user of this object, my interest in this microphone is something very simple. I'm saying it should stick to my head nicely, and that microphone should be quite close to my mouth, correct? And it should produce appropriate sound waves there. That is my intent. Whether it is made up of plastic or, it should not be made up of gold or something, that becomes too heavy, right? So I might be worried about the weight of that. Now weight should be tolerable. I'm not saying, I'm going to specify that exactly, saying it should be 4 grams or something. It is 4 grams, 5 grams, alright, but not 50 grams, right? So I got some limits there. So that means we would like to view every object in that particular fashion, saying that I am only looking at the externals. And this complexity also, complexity of real world systems. One thing we notice, when you say I've got a complex system, but then unfortunately for us, nature has got what is known as a hierarchy of expression of complexity. Hierarchy. Hierarchy is the other property of object-oriented systems, because that is actually a property of the realized systems. All real-life complex systems have what is known as a hierarchy. Hierarchy is the architecture of the system itself. I'll take a couple of examples. You take some solids. Let us take one solid. Take this pen itself, for example. You can cut it to several pieces. I get pieces of solids. Right? That means one object is made up of several small objects. You can see that that's the hierarchy or the architecture. So solids, I can take and pieces of solids I will get. Right? If I break down that solid, correct, I can look at it as several pieces of solids. Or I can break this down further, and what I get is some molecules. Correct? There are molecules in the solid. Right? I may not be looking at molecules when I look at a pen. Right? I am looking at some other property. But if I want, I can always look at molecules of the pen also. Right? I can look at the molecules. And if that molecules, if you break them further, you will get some atoms, even a smaller size kind of entities. And atoms, of course, you can break that down further. You get protons and neutrons and electrons and so on, which I suppose you can still break down further, and you'll get positrons and maybe something else. I don't know what else. Physics, they keep on discovering. There's no limit to this, I think. So this is the hierarchy of this. You take the solar system itself looks like an atom. Now you can see that. Now, so you got so many planets going around in circles. Here I got so many electrons going around in circles. The only thing is the size is different. It's just a reduction in size. That means that our nature has got that expression that we got these layers of complexity. Complexity is not one entire complex system. Actually, it's very simple actually. It's just got layers. If you look at one layer, it's quite simple. It is all the complication comes because of the several layers. So this hierarchy is layered architecture actually. That means when you look at a complex system, you can look at it as a series of layers. Each layer depends on the layer below. Like for example, molecules, piece of solids depend on molecules. Molecules depend on atoms and so on. But then you can look at molecules without worrying about atoms. You can look at piece of solids without worrying about molecules and so on. You can use each of the layers almost independently. Not 100% independently, but almost independently. That gives us the last picture for this language evolution is the object-oriented method only. But then now it's going to look hierarchical in nature. We got that architecture of the system saying that now I've got the several layers. I got several layers. Each layer has got one set of objects which of course interact with one another. Correct? Each layer has got its own set of objects, of course. And we notice that one thing is there when we look at the interactions. Within object, interaction is massive, right? This is the inner working detail. Object to object in the same layer, interaction is much lesser when compared to this inner working detail, is much weaker, right? And when you go across layers, for example, there is an interaction. It is even smaller than the interaction within the same layer. This interaction is even much more smaller. That means that because of that, we get the resilience in the software. Is that clear? It's almost like forces, physical forces. There are different kinds of forces. One kind is what we call the gravitational force. Now, gravitational force, I think, can be exerted at very large distances also, right? Light years it can exert. So stars can exert gravitational force. But then it is one of the weakest forces. Very, very weak. But it works across very large distance. Now you want a slightly stronger force, you have to go to electromagnetics. Electromagnetic force. Probably this magnetic force works for a couple of feet or something. Beyond that it doesn't work. But then I think it is probably million times stronger than gravitational force, right? Gravitational attraction. So definitely it is much stronger. But then it is closer, right? So as you go closer and closer, things are going to become stronger, right? So that is there. And as you go more and more distance, the interaction is going to be weaker and weaker. Exactly same thing happens. Or maybe you look at, next is what you call molecular forces. There is intermolecular. See, in the case of gases, for example, there is practically no intermolecular force. No? Molecules are simply going all over the place. There is no specific interaction. Whereas when you come down to liquids, they at least try to stick to one another. So there is some interaction there, but minimal. Whereas when you come to solids, there is a solid binding. Molecules cannot get out of one another's presence. So there is a solid binding there. So there is an intermolecular force in solids, which is much more than electromagnetic force. Actually, it is more than that. That's why you can't cut a pen like this easily, because there is that binding force which is there. But then it is much closer. No questions. And lastly, we come to intramolecular forces, which are popularly called Nuclear forces, we have seen a couple of examples in the recent days. What is the power of those forces, right? What it can do to human population, we have seen that recent times. So, nuclear forces are massive, but then they are restricted to only that nucleus itself, a very, very tiny part of that atom. Only those protons and neutrons and so on, right? So, that means, same way here, you can see that across layers, we got the weakest kind of interaction. That means I can quietly change one layer without telling anybody. Practically, you don't need to tell anybody, you can change one layer. No? That's the meaning of that. Correct. Suddenly one fine morning, all the bank clerks who are sitting there, they get replaced by new set of clerks. You think your business with the bank is going to suffer? Yes, sir. Practically, no. I mean, there may be one or two irritations saying as soon as you go there, somebody doesn't say good morning or something. It doesn't say it because he has not seen you before. But otherwise, I think basically business is not going to be affected. You can quietly change a couple of layers without telling anybody. Right? So that is one aspect. So the weakest kind of interaction. Then across objects of the same layer, I think there is a little more interaction. So changing one object there, other objects may feel bad, may be surprised, they are astonished, right? So we have to keep that astonishment as minimal as possible. Minimal astonishment is a trick actually. Correct? That is there. And of course, we go within an object. I think there the maximum interaction like nuclear force. We better change, if one change one line of code, anything may happen to that object. But then I think since it is a small area of code, if we are going to delegate the responsibility to only one person, one programmer, I think he or she could handle that. So we have no problem in handling that. So large packages now we can see, say I've got upwards of millions of lines of code, 10 million lines or 4 million lines of code. Only choice is we need to use this architecture because that is what is there in physical life. What this package is trying to imitate is a problem that the package is trying to solve. Problem itself has got that architecture, a physical architecture which is there. We should make best use of it. In that one, the best way of object orientation is thinking in the application area. Object-oriented thinking is very simple. Think in application area or application domain or what we call the problem domain. So whatever problem that you are trying to solve, don't think in isolation. Think in terms of the problem domain itself. You'll be able to identify the abstractions which are present. You take a bank, for example. One clerk is an abstraction, one customer is an abstraction. That slip of paper, that voucher is an abstraction. Correct? You can look at each of these and they're interacting with one another. Correct? So now, just thinking in the application domain itself is object-oriented thinking. That our brain is doing all the time to solve our day-to-day problems. All we are saying that, why don't you put that into a program? We're going to write a few pictures and put that into a program is all we are saying. It is being done already. It's just an analysis of that method, which is already familiar to our brain in day-to-day life. We only want to apply it to programming. Correct? So that is one aspect of that. Is thinking in application domain itself is one key aspect of object-oriented thinking. Now, what are these concepts of object orientation? I think primary concept is abstraction. No questions on that. That I already mentioned. Abstraction is the primary concept. Then we have a few other fellows like encapsulation. Already explained that bit of detail. Hierarchy is that what I showed you just now. Hierarchy is because most applications have this hierarchy architecture, and that we need to encash on that. We need to exploit in that feature of the application itself. That is modularity. Again, is that set of modules. Modularity, I think, is more in terms of distributing the task to several programmers and getting different files out of that, programmers and so on. And of course, just because you have architecture or hierarchy does not mean you cannot have modularity. You can still have modularity as part of large applications, object-oriented applications. I can still have modules. I can have one module which might have several objects, correct? One module probably goes across layers also, it doesn't matter. So, and modularity is totally different. It's physical, right? Modularity is physical in terms of the files which is going to contain the objects. That is the classes which represent the object and so on. I could have several classes in one module, correct? So definitely it's quite possible. Or I can have one class which goes across a couple of modules and so on. So definitely modularity is totally independent. And the class structure itself is totally independent. There are the two orthogonal dimensions which I showed you some time back in that development itself. Whether an object belongs to one class, which class or which module and so on. What is the combination is one thinking that you need to do. And whatever suitable style which is suitable for that application, I think is what you need to adopt, right? So that is another aspect of object-oriented thinking itself. Is that clear? I mean, approximately. Now, these are, of course, the essential features of object-oriented methods. There are three more which are suggested, like typing and concurrence and persistence, of course. These are not 100% required features of an object-oriented application, but they are desirable features of an object-oriented system. Maybe we can just talk about that for a couple of minutes. decomposition. I think I did not talk about that. Just talk of that. Actually, this addresses that same architecture or the hierarchy, saying that I would like to decompose a problem. Same object-oriented thinking. Let's say I got a large problem. First thing is we want to abstract out of it. Now we want to derive abstractions out of it. We want to derive layers out of it. We want to derive the hierarchies out of it. Of course, no questions on that. And once we do that, I mean, what is the method that we use for doing that? Is that decomposition method, sir. There are two decomposition methods which have been used. One is, of course, the classic style. Classic style is basically algorithmic decomposition. Algorithmic decomposition. And of course, this is the object-oriented decomposition. Is what we would like to do. Object-oriented decomposition talks of objects, and that is what is the object-oriented method that we employ. And the algorithmic is basically what we call the top-down approach. Top-down approach is basically the structured programming methods. When you get a big problem, don't worry if you can't solve it. Just break it down to smaller problems and let's try to solve each of the smaller problems. Even if the smaller problem is too big, break that down further and so on. So just a top-down approach that we use for solving. That is the algorithmic breakup, decomposition of the problem itself. And object-oriented decomposition is deriving abstractions out of that application domain, problem domain. Is that, of course, for a large application, not necessary that you must use only object-oriented decomposition. But frequently we find that you may have to do both, right? I mean, you can't just give up the traditional methods just because we got a new technique to use. We may have to use both kinds of decompositions, algorithmic as well as object-oriented decompositions of a large problem to say I need to develop one application for it. It's just a footnote. You can make a mental note of it. I'm sure that these things probably will be able to appreciate only after you start working on some live projects of object-oriented methods. You have to do some large live projects. Then only you'll be able to appreciate how to go about doing this decomposition. To start with, somebody has solved this problem, do the imaging system, do a voice recognition or whatever. So then how do we start? Where do we start? You have to start decomposing the problem. Even before that, you have to start thinking in the application domain. You have to look at the problem domain or the application domain. You have to understand the application first and see how your brain understands it. And out of that, you can start deriving the abstractions out of it, right? Out of the application itself. Abstractions must come from the applications. The way different aspects of the applications interact with one another, you'll be able to derive those essential features of the various aspects. Therefore, you are able to derive the objects and you are able to derive the abstractions out of the same application area itself. Let's say I want to look at objects or classes and what are the best candidates for that. Then you start doing decomposition of the problem itself. First is what are called entities. Best kind of objects are what are called entities. Entities are actually entities which are part of the problem domain itself. Take a bank, for example. Each person there, each worker is an entity. Manager is one entity, is a separate entity. Right? Manager is different. Clerk is different. Assistant manager is different. Each is a separate entity. Correct? That the entity of the problem domain itself can be treated as one object because internal working of the entity is a strong bind, whereas entity to entity interaction is a weak binding. Correct? Definitely that is there. You can always see, you can imagine that, right? And in fact, you have a layered approach also. In the case of a multinational company, for example, it's got several offices, correct? I'm saying there is some amount of interaction by one person of one office to one person of another office, another branch also, there is an interaction. But that is far less than an interaction of one person of one office to another person of the same office, right? There is much more interaction. In fact, if the person in the same room is likely to be even more interaction than if the person in another room in the same office, correct? You understand? So that means as the distance gets reduced, we find the interactions become more and more. That is how we need to analyze. And the entities or applications, I think, are best bets for deriving the abstractions and making the objects out of that application, right? That is object-oriented thinking. But then next best that you can think of are what are called one set of actions. Right? And a whole bunch of actions are going to take place. This addresses more on the dynamics of the system. So actions, you can put together one set of actions and abstract the actions. Correct? Action itself. Like milking the cow is an action, right? So we can abstract it, so that itself as an abstraction. Some actions we can always abstract. One bunch of actions. That also could be an object. Object need not be a physical object of data values. It can also be a set of actions. So that is the next best that you can think of. Then, of course, if we don't have either of these two, we can have what are called virtual machines. Virtual machines addresses to some extent this layered architecture also. Like what is normally done is you say I've got one layer. I would like to treat this lower layer. Let's say I got a couple of layers. I got a lower layer. Lower layer, of course, has got an implementation detail which is very specific to itself. But then our interest in the layer is not the implementation detail, but the way we can interact with that layer, right? Is the interface of that lower layer, which is also known as a presentation. Presentation, how it presents to upper layers, no? Is that is what is important. And we can look at that, we can study that and say what you could do perhaps is that this itself can be a virtual machine. That means you can implement a machine as a layer. No problem, sir. You can even implement a CPU itself as a layer if you want, right? So you can have a layer which imitates, this entire lower layer is going to imitate some kind of a machine. That is known as a virtual machine. And as far as upper layer is concerned, upper layer says, I want to work on such a machine, right? Such a machine is not available. You can give software for it. No? It's a simulation. That is what is known as a virtual machine. One simple example I'll give you. Live example is, virtual machine is this, Java. Actually Java, I am sure all of us have heard of Java. Java is just a CPU specification. Believe it or not. Java is just a CPU. It's a virtual CPU. It's not a CPU which people have manufactured. There is no central processing unit. But actually Java is a CPU. It has got one whole instruction set. Actually, like Intel 8486 has got one instruction set. Java CPU has got one instruction set. Only thing is nobody can manufacture CPU to execute those instruction sets. You can't execute those. You can't make a physical chip to execute that. What you do is write a software to execute that. No? So that becomes a virtual machine. In fact, what you have is the lower layer is simply the interpreter. That means this fellow gets the instruction set of the Java CPU itself as input and is going to execute that instruction set as it interprets those instructions, right? And the interpreter itself can run on some CPU. Doesn't matter. It can run on 8486 or it can run on an Apple or it can run on an Orange or whatever. No, so it can run on any machine. Does not matter. Whatever machine this interpreter runs, remember it's going to interpret the same instruction set of the Java, right? Now you can see that Java programs are universal. Binary code works on any machine. Provided for each machine you have the appropriate interpreter which interprets the same instruction set and does the job on that particular machine, right? So that machine, that interpreter, like we say in Kannada, correct? Correct, no? You understand? So Java is a virtual machine actually. It's just a CPU specification. You read a CPU specification, you have to read Java. Java book is one CPU specification. That is a virtual machine. It's also sometimes, like I said, it's sometimes useful. Definitely it's useful technique to use. We could use parts of our system as virtual machines. In which case, actually virtual machines, basically what it does is, we are writing a specification for the interface and we intend not to change it. Correct? For all time to come. And the implementation can keep on changing over a period of time so that we get better and better implementation. Right? Tomorrow I may decide to remove the quads from that clock and maybe put something else inside. But outside interface should not change. Otherwise students are going to get astonished. No? You understand? See, there is a question of least astonishment that we need to have. There is a question of essential properties. When you come to the classroom, for example, no? Classroom, you expect something, right? Where you can go and sit there and watch the instructor or lecturer and watch the board and so on, right? Of course, you get classrooms of different shapes. No questions. Round classrooms, square classrooms, rectangular classrooms and so on. But then our brain doesn't care. It says, as long as I'm going to be least astonished, it is alright. No? You understand? So that means that, that itself is known as what is known as a contract. This interface is known as a contract. As long as you don't change this contract is an interaction between a couple of objects. As long as the contract does not change, we are not worried if the inner working detail of an object actually changes, right? That is known as a contract, right? We would like to keep that contract as same as possible. Virtual machine is a 100% technical specification of the contract. That is known as a virtual machine. Sometimes it could be quite useful. But many times we do find that there are some assaulted stuff. It's not really abstraction, but then what you just put together a set of fellows and say, is an abstraction. Is an abstract abstraction. It's not really an abstraction, but we visualize that as an abstraction. It's just a set of assaulted topics we put together and say, we're going to treat that as one object. It's an assaulted object, really speaking. In fact, in one sense, a module, for example, is a simple example of an assaulted object. A module. Take a module, for example. A module in the modularity concept is internally, inner working detail of the module is tight bound, of course, but then across modules we expect some very weak interactions, right? Very weak interactions. That means a module is, when you say I've got a module, may have several objects inside, but then entire stuff you can treat that as an object. Because other modules know what to expect, correct? In the module, see, Uttara is not just Shastri, Uttara is this classroom, Uttara is that lab room, Uttara is that manager there, Uttara is couple of office boys, Uttara is not having water in the toilet many times. See, all of this is Uttara, right? That is the module, no? Why? And the only purpose is you should be least astonished. That once we satisfy that, people are happy, right? So they can interact with the particular object. A module is something like an assorted stuff. It is the least favored kind of abstraction that we plan to use as part of the application domain. But then entities, I think, are the ideal kind of objects because they interact with one another. Objects go out and start doing stuff to other objects and so on. So it's a very interesting aspect of object-oriented thinking is to identify the objects in the application domain, in the problem domain. So that is what we would like to be able to do. So that is what comes off this object-oriented decomposition, when you do thinking in the object-oriented side. Now, when we look at a couple of other aspects of object orientation, which, see, all the earlier ones that I mentioned so far, abstraction, encapsulation, modularity, hierarchy, and all this, they are supported by C++. That means they are enforced by the language. Language enforces all those features. Whereas, this concurrence and persistence, for example, these two, they are not actually enforced by the language, but then you'll have to be like a C also. C also you can do hierarchy, right? But C does not enforce a hierarchy. C does not enforce encapsulation. Same way C++ does not enforce concurrence, or there is no provision for writing a concurrent object in C++, or persistent, for example. These are not directly supported, but you can always write a program in C++ which supports concurrence as well as persistence. So these are slightly lesser desirable features of object-oriented programming, but C++ does support them, but then it is a programmer's effort. Language is not going to lift a finger to help you do this. You have to do it yourself, as part of the programming. Now, typing refers to the data typing. Typing is actually data typing. That means, we are looking at data types now. Like an integer is one data type, correct? Double precision is another data type and so on. Data type is different kinds of data, right? So we got languages, which support, what is known as, the typing of a language can be very strong. Strong typing really means that you cannot do an operation on an object if the type does not match. So typing, let's say int, for example, I can add a couple of integers. Correct? Because I got a couple of names, for example. You can't add a couple of names. How do you add names? You can't. There are two different types right now. So it's me trying to do an operation on a data type for which the data type does not support the operation. If that is enforced, language enforces such an operation cannot be done in strong typing. Language itself will stop you if you attempt to do that. It's called a strong typing. In fact, I think IFL is a language which supports very strong typing. IFL, object-oriented language, does not allow an operation on object unless the object has got that operation, right? Whereas, you can also have weakly typed language, weak typing. And one of the the most popular weak type languages is the original OO language, is a Smalltalk. Smalltalk allows anything to anybody then. You want to try to eat one pen, you go and attempt it. If it doesn't work, sorry. Correct. You understand? Normally you say, I want to eat a pen. This fellow won't allow, no? IFL won't allow. Saying, you can't eat a pen. You can eat an ice cream, but not a pen, no? That is, pen is not eatable. No? It doesn't have the eatable operation. So, it's not going to support it. Whereas, weak typing fellow says, you do what you like. At execution time, you are in trouble, no? Sorry. So, you attempt to do any kind of operation on any kind of object. It's called weak typing, right? So, strong typing, I think, is better because, you find that, the fellow will not try to allow you to do funny stuff, right? So, discovering late in life saying, no, what happened? I'm very sick for the past 1 month. Why? I ate one pen. Nobody stopped me, no? So I'm saying at least somebody stopped him, you won't be sick today, right? So I think strong typing is always advantageous. C++, I should say really strong typing, but then, it is really hybrid. Hybrid. That means, hybrid because you can also do some weak typing in C++. But fundamentally it is strong typing. Language is only strong typing. But then we have this, cast operation, casting. This casting, by using casting, you can practically do anything that you want on any object. You just have to cast, use the appropriate casting. So because the cast operator, it actually is an hybrid typing. Occasionally we require this weak typing, but then most of the time I think strong typing is what is good, in terms of, a sturdy language. If I write a program, I'm sure he's not going to do some funny stuff, at the execution time, is to have strong typing. So most of C++ is strong typing. Occasionally we may resort to some weak typing. Especially in the case of libraries, I think sometimes you may have to do weak typing for which casting is going to be used. Casting, as long as it is used sparingly, is alright. Please don't use it in every line of code, right? So that should be avoided. So that is one aspect. And one more thing is, if you say I've got an action Action is, of course, a set of instructions, right? I got a set of instructions. These instructions are going to operate on some kind of a data box, right? So, some kind of data, right? This is what is there. And this action, we have a property which is called binding. Binding refers to the binding of the instructions to the data. So, what data these instructions are going to operate on is known as binding. And we got two kinds of binding that are employed. We got what is known as a static binding. Static binding means at compile time itself, the compiler decides what data these set of instructions are going to operate on. It's called static binding. And we have the other kind of binding, which is dynamic binding. Dynamic binding really means that the binding of data to the instructions is decided at execution time. Advantage of dynamic binding, of course, C++ supports dynamic binding. Ada, I think, does only static binding, so it's got a couple of problems, limitations. C++ does dynamic binding. Reason is, once you can do dynamic binding, that means the same set of instructions today may be operating on these data today. Tomorrow when you run the same program, the same instructions can operate on different data. So there is the advantage of dynamic or late binding. That is what C++ supports. In fact, this late binding or dynamic binding is necessary for one aspect of programming which is called polymorphism. Polymorphism, I suppose we'll have to discuss the details at a later stage. Polymorphism is one word for saying object-oriented programming. Is polymorphism. There is no difference. Practically, there is no difference between object-oriented programming and polymorphism. And to support that, we must have a decent dynamic binding. And of course, that becomes part of the language specification. C++ has such dynamic binding, but then it supports hybrid typing of objects. Mostly strong, occasionally weak. Right? See, C++ would like to give you that eventual facility of doing a weak typing also, but encourages you to use only strong typing, because strong typing is good for health, I think. Okay. That is on the typing. Now we'll take concurrence. Concurrence, I think, refers to, what is concurrence? Concurrence is simultaneousness, no? Some kind of simultaneousness. Is, if you say object, you say I've got an object, there are two kinds of objects that you can think of. One kind of objects are called active objects or animate objects. They get up and start doing things on their own. No? Active fellows, right? Like Shastri. Shastri will take the pen and start writing on the board and start talking. He's an active fellow, right? Sir? Whereas we got other kind of objects which are called a passive object, right? Passive means like this pen. Pen is there only. As long as somebody doesn't pick up and write, pen is there only, right? He's a passive fellow. So he's basically inanimate, right? So we got two kinds of objects. In terms of programs, if you look at programs, we have, if you look at the programs, we have what is known as a mainline code. No, mainline is actually basically the main procedure definition. It's a main procedure definition. Maybe main invokes another procedure definition is also mainline code. In fact, our entire program is what is known as a mainline code. No, is what is known as a thread of control. This is a thread of control. I mean, CPU is basically the program counter of the CPU is what we are saying. No? That is the activeness. So that means it is executing some object code. Is that thread of control? That object is doing stuff, right? So there is only one main line, obviously, as part of any program. So that is the main line. That is the active object. Main line is the active object. Anything else is passive, right? Passive objects, no problem. Of course, if you have multiple active objects, I think you are in a bit of a trouble, no? Supposing this pen is just simply sitting in one place, pen is walking all over the place, and Shastri wants to pick it up, pen is gone there, no? Want to pick it up, it has gone there. See, you've seen that in movies, so. See, that is difficult. Interaction between two active fellows is always more difficult than interaction between one passive fellow and one active fellow. Right? So, in fact, in most of our programs, we find only one active fellow, so we go and pick up things and do it. No problem. But then occasionally you do have some things which are called interrupts also. You have interrupts. Maybe you got one keyboard interrupt, or maybe you got one timer interrupt, or you got one mouse interrupt, or maybe you got one hard disk interrupt, whatever. So, depending on the system, you have different interrupts. What is an interrupt? Interrupt basically is asynchronous, right? Asynchronous. That means regardless of what the CPU is doing at any point of time, suddenly CPU is going to jump off to the interrupt service procedure, execute it, come back and continue, right? So interrupt is basically one active object, right? So it may happen any time, right? So that means we got the concurrent execution of interrupts and the mainline code is that multiple active stuff. Is what is known as a multiple thread, no? When you have multiple threads, I think problems are more complicated. See, when you have multiple active objects, there are two ways actually. One is you have a single CPU, of course. Single CPU can only have concurrent threads. Concurrent. Concurrent means not quite simultaneous, but because of interrupts, it may happen anytime kind of threads. So it's called concurrent. Whereas when you say I got multiple CPUs, you can actually have multiple threads, which all of them are executing at the same time, not just concurrently. I think problems are going to be even more compounded when every fellow is simply doing, he's like a boxing match, yeah. So I just want to hit you, the way I hit must actually kill somebody, right? Yeah, but it doesn't kill anybody because that fellow has just walked out of that place. So you can see that boxing is like that, multiple CPUs. Both the fellows are trying to do at the same time, right? So definitely, I think writing programs for multiple threads or concurrent threads is more complicated than writing program for a single thread, right? So concurrence, bringing concurrence to objects, that is have multiple active objects, I think is a difficult exercise. We need to do a lot of checks in the software and so on. It's not a simple job. C++ does not have a direct support saying this should be on a concurrent object or this should be on active. You can't declare an object to be active or passive. It doesn't exist as a syntax in the language itself. But then we need to do that also. Some applications like typically, it's got one large online transaction processing systems, for example, like a airline reservation system or whatever, air traffic control system and so on. Multiple planes are landing, right? You better control, man. Don't say, no, only one plane should come at a time, I will work. No, so that is not possible. So such large applications, we realize we need concurrent threads, or we might even need multiple threads and so on. Programming those is not straightforward. It has got its own problems, right? C++, you can do those programming, but it is an effort on the part of the programmer. That is on concurrence. Then lastly, I think we have persistence. Persistence refers to lifetime of an object. Refers to lifetime. How long that object lives, lifetime of the object. In fact, we can list a set of objects or items in increasing amount of lifetime, increasing persistence. The lowest persistence are what are called temporaries. Temporaries, for example, you say I want to write one statement, x equals a star b plus c star d semicolon. One simple statement. When the compiler wants to evaluate this, or the program wants to evaluate this, he's going to say I will multiply a and b within one hand. That's a temporary. Right? And I'll multiply c and d and then add the two together. At the end of this statement, the value which I computed for a star b, for example, I don't need to care about it. It can disappear, right? So it's a transient value, transient or temporary. Is valid only during one statement execution. So it's got a very small persistence. It doesn't persist beyond that point. But then if you want slightly longer persistence, you have to go for what are called locals. Locals is very simple. You open one context, open brace, and declare one symbolic reference, let's say int x semicolon. And as long as the CPU is inside this context, x is going to exist. But then as soon as CPU exits from this context, once the CPU hits the close brace and gets out of this context, local is going to disappear, right? Local has got the scope of this context. That means local is there only as long as CPU is inside this context. It's got a longer life than temporaries, but it still has got a short life. Local is going to die, right? It's going to be removed from the stack. So these locals basically are going to sit on stack. No questions on that. Then he said, no, I don't want these fellows to disappear. I want even longer persistence. Is globals and static. Globals are static. For example, you declare a symbolic reference right on top outside any context. Let's say I got an int total semicolon, and in the entire file, for example, you can use that total is there. It's not going to disappear. These are basically on a heap. These are on a heap memory. They don't disappear. They don't appear and disappear like the stack locals. They are there always, right? As soon as the program starts, the total is available. Until the program ends, it is available. No? So in fact, these are for duration of one program execution, of course. It's for duration. So they persist till the end of the program execution. Till the program ends, the fellow is there, is available. So it persists for the entire duration. But many times we find even that is not sufficient. We want even a higher persistence. Remember, tomorrow you run the same program, the total value is gone. Once the program stops, that is gone. So next time when you execute a program, you have to recalculate the value, right? It doesn't persist beyond one execution. But then we might want some objects which persist across executions of program. How do we do that? Use the files. File data. So file data are there. As long as you don't remove them, they're going to persist, right? So that means I run the same program tomorrow, the data is still available. All the records of a file, for example, they persist across executions of that particular program, right? The same program can use it on several days, on several executions. But sometimes what happens? Programs are being maintained. We release different versions of the program. We modify the program. When you modify the program, can I go back and use the same old file data, or I think I cannot use it? Can this data persist across versions of program. Usually our typical data cannot. No, when the program has been modified, probably can't use the same file structure and so on. But you say, no, I want it to persist beyond. I want it to persist beyond the versions of the program. Definitely we need these file data are all right, but then I think those file data also you have to design it in such a way. It will be very carefully designed so that they can be used across different versions of the same program. I should be able to write different SQL queries in Oracle or something. Can use the same data file, right? It actually is persisting across different versions. Definitely that is the highest persistence that you can think of. But then beyond this point, for example, C++ supports only here. C and C++, they stop at this persistence that is for one program execution. Anything beyond this place is basically some kind of a database technology. Database technology is where we worry about persistence across executions, persistence across different versions of the programs. They refer to the database technology. Of course, it's a totally different issue. All your relational databases and so on. But then databases also have grown in size. Earlier databases were small size, 50 megabyte, 100 megabyte. Today we have got databases which are gigabytes in size, right? So databases have gone through the same growth phase. Now we got colossal databases, right? Take any internet itself. You can see the size of that database of even just the number of sites. Now websites is colossal, right? So when you go into colossal database size, I think database fellows also have had problems. Database technology fellows also have had problems. So therefore, today I think you have a marriage between two technologies. We have object orientation and also database technology combined together to get what are called object oriented databases. So that is a combination of two different kinds of technologies. Anything beyond this point, I think it refers to OODs, OODBs actually, object oriented databases, which make use of both database technology as well as object orientation. That means C++ really does not do database, it only does object orientation. We need to add some further techniques and codes and special programs and special libraries to the C++ program to handle these databases and database technologies and so on. So that is also quite possible, of course, but then I think our discussion in the classroom, I suspect is going to be limited to only the first three kinds of persistence, temporaries, locals and globals. I think we don't want to talk of this across executions. Probably this file data as a simple persistence. We say I would like to keep my objects in the file and get them back tomorrow and so on. We might hope to add this as part of our project so that you can work that kind of persistence. Or you have to write a code for the persistence. Unfortunately, C++ doesn't automatically support it. So you have to write that persistence code for getting objects to go and sit in the file today. And tomorrow quietly will come back from there also. And continue from that point onward. So that I think we can add that as a part of our project, live project that we plan to do.